Hello, everyone. Today we're going to be talking about materials. So, how do we pick a material? I'm hoping that some of you guys have given thought to this as you're doing work around the house, maybe, or working on something that you're trying to fix. And you say, how do you pick a material? So, the first question that we must ask ourselves is, what are we trying to build? And then, what properties must the material possess? So, as an example, if I'm trying to build something that is going to take a lot of abuse, I have to build it to be pretty strong. But if I'm building something and I want the lightest possible weight, I may be able to get away with it not being as strong. So those are a couple of the things that we would look at. As an example, if I'm building an airplane, it's got to be light and strong so that it could fly. But if I'm actually building a table or a work table per se, I want it to be heavy and strong so that it doesn't get moved around as I'm working on it. So I'm going to start and talk about the phases of matter. Matter can exist in any one of four states, either a solid, a liquid, a gas, or a plasma. And all matter can exist in any of those four states depending on the temperature and the pressure that that material is under. So, for example, water, which we are all aware of because it's all around us, is a solid below 32 degrees Fahrenheit or 0 degrees Celsius. And solid water is called ice. So we've all seen ice during the winter here in Westchester County, and it's solid, right? If you fall on the ice, it hurts. Um, Above 32 degrees Fahrenheit or 0 degrees Celsius, water becomes a liquid, and this is all under standard atmospheric pressure. But water becomes a liquid, and so between 0 degrees Celsius and 100 degrees Celsius, it's a liquid. And that's why, we drink water because at room temperature, it's a liquid. Um, some of us like to go swimming or boating and playing in the liquid water, and that's all around us also. Um, Above 100 degrees Celsius, water changes into a gas, and gaseous water is called steam. In engineering, steam is used for a lot of things. When we were talking about electricity and power generation, I mentioned that all conventional power plants operate by having a turbine that is moved by steam. It's spun by steam, which then in turn spins a generator, which generates electricity. So again, gaseous water is called steam. We use steam for a lot of reasons in engineering. If I keep adding heat and I get above 2000 degrees Celsius, the atoms will break up into free electrons and nuclei, and we will have what's called a plasma. So I'm going to talk now about some general material characteristics. So first one that I have on the list is strength. I mentioned before that we look at how strong an item is depending on what we are going to be doing with it, right? Interestingly enough, if you look at like hangers for paintings or pictures, they generally will have a weight um, limit on them because again, if I need to hold something that's heavier, I need something that's stronger. But if I need to hold something that's small, it doesn't have to be very, very strong. Um, Funny little story. Years ago, when my son was playing Little League Baseball, we went and bought a chair couple chairs that we could use while he was playing to sit down and watch the game. And when I got home and I opened the box, inside it had a label on it, and it said, warning, weight limit 200 pounds. And I thought about that, and I said, building a chair in the United States with a weight limit of 200 pounds, maybe that's not actually strong enough for what we're trying to do. So that is, like I said, one of the examples. Then also weight. So again, weight matters when I'm building something depending on what I'm trying to build. I've mentioned before, I like to go mountain biking, and in bicycles, the weight is actually a big consideration because we are the engine in that bicycle. So the more weight that I have to move around, the more difficult it can become, especially when I'm going uphill. There's then that balance between the strength and the weight, right? We used to joke around in engineering, per se, that strength, I want it strong, I want it light, cheap. Pick two, right? And that's basically saying that I could build something that's strong and light, but it's probably going to be expensive. I could build something that's strong and cheap, but it's probably going to be heavy. Or I could build something that's light and cheap, but it probably won't be strong. And again, that's a generalization. As we are moving forward, we're using different materials that have different characteristics. And, we are getting close to attaining some of that where I can have all three. Flexibility. Flexibility is how much a material will bend when I'm applying a load, right? And so in certain conditions, I want flexibilities, but in others, I really don't. So the next item on my list is electrical conductivity. So if we have something like the cord, the power cord for either a tool or your computer, an appliance, whatever it is, we need the inside of that power cord to conduct electricity so that it can get from the outlet to whatever the device is that we are powering. But we want the outside of that cord to be an insulator because we don't want to get electrocuted as we're using that product. So depending on what we're trying to do, we have to look at the electrical conductivity of the material that we are using. Then I have heat conductivity. Similarly, metals are very good at conducting heat as they are in conducting electricity, but there are applications where I don't want heat to be conducted. I don't want the heat transfer to be slower. So, such as an insulator in the walls of our house, we don't want to conduct heat. I actually was very interested to find with an infrared camera, if you take a picture of a house, you see every single stud. And if you're using metal studs, you see them even more so because of the fact that they conduct heat at a different rate than the insulation that is there. So if I'm going to build something that like an oven, I want to make sure that the heat is not conducted to the outside so I don't get burned being outside, but I want to keep the heat inside or something like that. Corrosion. Now, nowadays, corrosion is thought of quite a bit, and it is actually rare to see a car that is relatively new driving around corroded. But that was not always the case. If you go back to the 1980s even, cars would tend to rust before they would wear out otherwise. Before the engine would fail or whatever, they would tend to rust out. And after that time, a lot of consideration was taken into protecting something from corrosion. And one of the things that they did with the cars was they actually started coating the inside and the outside of a body part so that corrosion wouldn't happen. Corrosion is actually an electrical reaction in a way, and you need the ions, and you need that electricity to flow from a cathode to an anode for this to happen. And so by putting in a barrier such as the paint, that could stop corrosion from happening, or at least slow it down from happening. Similarly, in some cases, if you have a device that you might want to make sure it doesn't corrode, there are systems that will put a small flow of electricity in the opposite direction through that to help it not corrode. This is something that I saw when I worked out in the field with certain pipelines that were in certain critical situations, that they actually applied a small current to keep them from corroding. And as we continue, we talked about electrical conductance, but we also look at electrical resistivity. So how resistant is something to electricity flowing? Resistivity is given in ohms, right? That's the unit of measurement for resistance. And when we look at it, you'll see something rated in the number of ohms. You guys are working on the second project now for this class, but there are resistors that are included in the kits that we have, those little Arduino kits, and they are rated in how many ohms. So what happens is if I have something like an LED, but I don't have a resistor in front of it, too much electricity will flow through that LED. So I need that resistor to kind of, slow down the flow of electricity. Similarly, if you look at something like a speaker wire, it is rated, or a speaker wire or a speaker itself, it's rated in its resistance in ohms. And amplifiers are actually designed, and the power ratings are given generally at 8 ohms. So if you're using a 4 ohm speaker, you probably get more wattage, but you may get more distortion and something because it'll allow too much electricity to flow through. Density. Now, density basically is weight per unit volume or mass per unit volume. So the denser something is, the heavier it is for the same size as a different material. The next item on our list here is the modulus of elasticity, or Young's modulus. And for anyone that is thinking of studying civil or mechanical, that is something you will see quite often when you're doing calculations. And basically it tells us the resistance to bending, right? And so when I'm looking at, if I have a beam and I want to see how much of a load it could have, there's equations depending on how the beam is set up that include that modulus of elasticity. And so what that is telling me is that is a material characteristic. So different materials will bend differently, even if they're the same shape with the same loading, right? And we probably all know this or have seen it, because if I have a block that is made out of wood and one that is made out of steel, the wood is going to deform and bend more than the steel is because of the modulus of elasticity is much lower. Just as an example, for steel, the modulus of elasticity is approximately 30 million psi, and for wood, it's about 1 million psi. So that's quite a big difference there. The modulus of rigidity tells me how strong something is to being actually overloaded. That's really what that looks at. The tensile strength in steel tells me how much of a load I could put on a bar of steel before it actually stretches and fails. And then the compression strength is how much of a load I could put on it to compress it or squeeze it together before it will fail. And certain materials are strong in tension and others are stronger in compression. As an example, masonry, so stone, concrete, is stronger in compression than it is in tension. Steel is very strong both ways, but actually stronger in tension. The modulus of resilience, again, is how much I could load something and it'll come back to its original shape. Modulus of toughness is how many times can I overload something before it actually fails. So the strength to weight ratio tells me how strong something is with relation to its actual weight. So I mentioned before the difference in the modulus of elasticity between steel and wood, but one of the things that I found very interesting is that steel and wood actually have similar strength to weight ratios. So that I found that interesting. I hope some of you guys may find that a little interesting. I have here thermal expansion. Anytime I actually heat a material up, it will actually grow. It will get bigger. And that is given by a term that we use, it's alpha. So I could tell you how much something is going to expand for every degree Celsius or every degree Fahrenheit that I increase the temperature. So we know this, and this is something we have to design for in stuff that actually sees quite a big difference in temperature. So something like, your car engine is an example where I could have a significant amount of thermal expansion because I could start up the car and it could be 0 degrees because it's freezing outside, and then within a matter of minutes I'm up to 300 degrees and in that car. So I have to make sure that things are designed that when it does expand, I don't have too much resistance, I don't have interference somewhere else, all of these interesting things. Heat capacity tells me how much heat something could store. So when I'm putting heat into something, they'll store that heat, and then when the outside temperature actually drops, they'll start releasing that heat. But the heat capacity tells me how much heat they could actually store. Viscosity is a characteristic of a fluid, which tells us how resistant it is to flowing. You may be familiar with that number when you start looking at something like motor oil, because that is given a viscosity rating. And generally with motor oil, the higher the number, the more resistant to flow it is. So I have, as an example, I like to joke around because one of my transmissions takes straight 110 weight gear oil. And my joke is I could, knock the bottle over and I still have time to go into the kitchen, grab myself something to drink down an iced tea, and then go back, and it still wouldn't have spilled because it's that thick. Whereas, the 20 weight oil that is commonly used now for engines is very thin and is not that resistant to flow. Vapor pressure actually tells us how something actually evaporates, right? So if I leave a dish of water and a dish of alcohol out in a room, they're both going to evaporate, but they're going to evaporate at different rates, and that's their vapor pressure. My bulk modulus of compressibility tells me how much something resists compression. So on this table, I have my modulus of resilience, and my E is my modulus of elasticity for different materials. So you can see here, steel, like I said, is 30 million psi. Aluminum is 10.5 million psi. Copper is about 16 million. And rubber is 150. So rubber is not that resistant to bending, and that's why you don't see too many beams and structural supports being made out of rubber. So we have various classes of materials. The first class of material I have listed here is metals, right? So metals as a class that have certain characteristics. They tend to conduct electricity and heat very well, and they tend to be fairly strong. Then concrete is its own class of material. In construction, wood is used in a lot of construction, so that's its own class. Plastics, something that was not that common 50 years ago, but now seems to be all around us. Silicon, on the electrical section, I mentioned silicon because it's used in semiconductors. So our computer chips are made out of silicon. Glass is its own class of material. It used to be thought that glass never actually hardens and does flow, but recent studies show that that's not actually true. Composites is a different class of material, and composite is made up of various different materials together. So an example of this is carbon fiber that we're probably all familiar with, which consists of carbon fibers and a rosin that is put on the carbon fiber to keep its shape. But without either component, you have no strength. Another composite that has been used for a number of years is fiberglass. That is also a composite, and similar, it has glass fibers, and they are mixed with a rosin that hardens and keeps its shape. When we're dealing with metals, we tend to split them up into ferrous metals and non-ferrous metals. Ferrous metals are anything that contains iron in it. So one of the general things with iron is it tends to be magnetic. So steel, iron, cast iron, they're all magnetic materials. So steel is an alloy of iron that has less than 2% carbon in it, and cast iron has more, and they're both ferrous materials, steel and cast iron. If you've worked with either of them, steel tends to have flexibility, cast iron tends to be brittle. If you've ever seen how they actually cut a cast iron pipe, what they basically do is wrap a chain around it, and the cutter is a chain, and as you click and click, it just keeps getting more pressure on the pipe, and the pipe will crack right along the chain. So they're a little different in how they're alloyed and made. They're both based on iron, but they end up with different characteristics because of the other materials added into the alloy. And non-ferrous materials are metals that do not have iron in them. So examples of those are copper, titanium, aluminum. Those are generally things that you'll see being used in construction and in engineering. You'll see those materials. Titanium has gained a lot of popularity lately because of its strength to weight ratio. Titanium is actually not as strong as steel, but it has a much higher strength to weight ratio. So I could build something out of titanium that weighs less than its steel counterpart and is still stronger. Aluminum, as we saw, has a modulus of elasticity about a third that of steel. So, when we're designing something made out of aluminum, we have to take that into account. But it is also about a third of the weight of steel. So we could make something that's strong and light, and a lot of that is being used now to make certain cars much safer. They're using high strength aluminum in certain applications to absorb energy from crashes. So plastics are used in a very large number of products. It can be considered one of two broad types. Thermoset plastic cannot return to the original shape once it's cooled. Examples include polyurethane, polyesters, epoxy resins, and phenolic resins. Thermoplastics can be reheated and returned to their original shape. Examples include polyethylene, polypropylene, and polyvinyl chloride. And I'm going to also include this link separately so you guys could please watch this video on how certain plastics are made. Now, we've probably all seen these symbols on the back of products. Look on a bottle or a bottle for anything that you have around the house, and you'll see a little triangle with a number in it. 1, 2, 3, 4, 5, 6, 7, right? So 1 is telling you that this is polyethylene terephthalate. The thing with that is generally used in soda bottles, water bottles, shampoo, peanut butter jars, those kind of thing. Number 2 actually is high density polyethylene. So you'll see that in milk and water jugs, grocery bags, those kind of things. Number 3 is vinyl. Number 4 is low density polyethylene. So 2 is high density, 4 is low density. And as it says, stuff that's used for is frozen food bags are generally low density, or squeezable bottles. Like if you get ketchup in a squeezable bottle, it's generally a low density polyethylene. Number 5 is actually polypropylene. Number 6 is polystyrene. So you'll find stuff like certain egg cartons are made out of polystyrene. And number 7 is other, right? So when you are recycling plastics, right now, Westchester County will take any of these numbers and they'll recycle them, but not every town does. So make sure that whatever you're recycling is recyclable. So silicon is used in semiconductors. Without these, we'd have no microprocessors. I'm going to give you this link. Please follow the link and watch the video on how silicon semiconductors are made. And then composites. And I will tell you the first video link here is to me, very fascinating to watch. And you'll see the difference between carbon fiber and steel in this video. So carbon fiber can be very strong and very light. It could also be very expensive. And it is used in demanding applications such as fighter jets and race cars. That video actually compares a carbon fiber drive shaft to a steel drive shaft, and they test them to destruction. And when you watch it, you'll see that the carbon fiber actually is 4 times stronger than the steel and weighs significantly less. So these are the kind of characteristics that we have with carbon fiber, or we can have with carbon fiber. And so in certain applications, that could become very critical. So fluids, in engineering, we also use fluids. Air is a fluid, and it's used to cool and to heat. Also used to run tools, turn equipment on, and all sorts of other things. When we're dealing with air, humidity becomes a very important factor, and humidity is the amount of water vapor in the air. And in certain tools, if the air has a high level of humidity, it will actually damage the tool and the tool will fail. So we have to actually put certain things into our airlines to get that humidity out of there to make sure that we're running at the humidity level that's not going to damage our equipment. Water. I mentioned earlier that in every conventional power plant, water is heated up to make steam and it's used to produce electricity. But it's also conventional. But if I look at hydroelectric, I'm also using water, and I'm using the potential energy in the water as it flows over either a dam or a waterfall, and I'm producing electricity. So that is one thing. And then on the opposite side here, I have high pressure water can be used to cut metals, to cut marble, and we've probably all seen that in some of the shows. I like watching shows on how things are built, and they will often show them cutting stone with high pressure water. So it's one of those things that we could see around us if we look. And I'm going to put the links separately onto Blackboard, and I'm hoping that everybody gets a chance to watch all the videos, and I hope you enjoyed this lesson. Thank you.